Hey everybody, I hope you are all doing well. We are on to the 4.4b notes, and this is more neat to the infinity optimization problems. And we won't get through all of these today, guys. It's a booklet of quite a few big questions. But I'll do a few of these examples for you, and I will send you a set of notes that has all of it filled out, as well as a blank copy that you can watch the lesson and copy down the notes if you'd like to do it that way as well. Okay, here's example 1. Find the radius and the height of the right circular cylinder of largest volume that can be inscribed inside a right circular cone with radius 6 centimeters and height 10 centimeters. Okay, so we've got to have this right circular cone, which looks like this. Right circular cone. Like this, and it wants to know, okay, the right circular cylinder of largest volume that we can inscribe inside this. Okay, so remember, inscribed has to be completely inside the cone. And a cylinder is like a can of soup. So this would be down like this, not going outside the cone. Okay, and so this is the situation, and it wants to know, okay, what's the biggest cylinder that we can fit in here? Okay, the largest volume. Okay, and it said that the height of the cone is 10 centimeters. And the radius of the cone is 6 centimeters. Okay, and so that's what we know so far. Okay, and we want the right circular cylinder of largest volume. Okay, so we want to maximize the volume of the cylinder, and the volume of a cylinder is given by the formula pi r squared h, the area of the base, times the height, and you might notice that just from the diagram, remember the cylinder cannot go outside the cone, and so the radius of the cylinder, I mean, realistically it has to be greater than 0 first of all, but it would have to be less than 6 as well because the radius of the cone is 6, so we can't have the red cylinder going out beyond 6. And also the h has to be greater than 0, realistically, for it to be a cylinder, and it can't be taller than the 10 centimeters that the cone is. So h has to be between 0 and 10. Okay, so that's what we have so far. And remember, guys, inside our main equation, this volume 1, we don't want to have two variables, r and h. We need to get rid of one of those. So we have to come up with another equation involving r and h. Okay, and the r and h we're talking about is the r and h of the cylinder. So like there's the height of the cylinder. and here's the r. Okay. And what we're actually going to do is we're going to extend this line all the way up to the top, and we're going to use what's called similar triangles. And we need to notice that this little length right here is actually going to be 10 minus h. Okay, because the whole thing is 10 and the height of the cylinder is h. So if I were to go like the whole 10 minus the h, that would leave me that little piece there. And then we've got the r. And so the similar triangles that we have would be this, that little one up at the top, the little 90-degree, and it has the 10 minus h side and the r side. So that little triangle, and then the other one is the big 90-degree triangle that goes like from the top of the cone all the way to the bottom. And of course, this whole thing, I'm basically going from the top of the cone to the bottom, so that's 10. And then I'm going from the center of that circle at the bottom to the edge, so it's the radius of the cone. So those are my similar triangles. Okay, and we know that they're similar triangles because you can see they have the 90-degree angle in common. But because this radius, this blue radius, is parallel to that red radius, then it would make this angle equal to this angle. Okay, so this angle equals this angle, and that forces the third angles to be equal. Okay, and when you have two triangles with all equal angles, they're called similar triangles. And the property that results from similar triangles is that the sides are proportional. Okay, it means that the larger triangle is a certain multiple of the smaller triangle. And so you can set up a little relationship like this. Maybe I'll do it in the upper right-hand corner. There's a number of ways that you can write the relationship. I guess we could do it like this. 10 divided by its corresponding side in the red triangle, 10 divided by 10 minus h would be equal to the 6 radius divided by r. Okay, because the bigger triangle is a multiple of the smaller triangle, and so all of the sides of the smaller triangle would get multiplied by the same thing to make the bigger triangle. So the sides are proportional like this, and in this situation we can now cross multiply, and we can get 10r is equal to 60 minus 6h if I multiply the 6 onto the 10 minus h. Okay, and I think in this situation, guys, it might be easiest to get h by itself, because then we can just go and plug in for h here rather than having to plug something into r squared and FOIL and stuff. So let's get h by itself. I'm going to subtract 60 from both sides, and I'm going to go 10r minus 60 is equal to negative 6h. And then I'm going to divide everything by negative 6. The h is now by itself. Negative 60 divided by negative 6 is positive 10. And 10 over negative 6 in lowest terms is negative 5/3 times r. And that's what we can use to go and plug into our main equation here. Okay, so our volume function is pi times r squared times 10 minus 5 over 3r. Okay, and we want to find the maximum volumes. We want to find the extreme values of this function, and the extreme values occur either at the endpoints, we're going to do those r endpoints because our function is in terms of r, or at the critical points. So we have to find the critical points of this. So first of all, the volume function, if we kind of clean it up a little bit, is 10 pi r squared. And then here we are going to get minus 5/3 pi r cubed. Okay, and so then we have to take the derivative of that, find where it equals 0 and where it does not exist, if possible. And those will be the critical points. And then we test the critical points and the endpoints. Okay, so v prime is going to be equal to, pi is a constant, but r is the variable, so we do the power rule with the r squared. 2 times 10 pi is 20 pi, and then the power of r goes down by 1. 3 times negative 5/3 would just be negative 5, and then we've got times the pi times r squared. So there's our derivative. There are no problem points for r, so there's no points where v prime does not exist. So where does v prime equal 0? Let's try factoring by GCF. We can bring out a 5 and a pi and an r, and have left over 4 minus r. Okay, and so then r is equal to 0 out of this term. What do you have to put in for r to make the whole thing 0? I'd have to put 0 there. And r equals 4 out of the 4 minus r bracket. Okay, so let's test endpoints and critical points to find maximum volume. So we're interested in the volume when r approaches 0. That's an endpoint. Okay, and that's also a critical point, so we're testing that. So we're interested in the volume as r approaches 0, interested in the volume as r approaches 6, and the volume when r is 4. Okay, and so we'd plug those values in for r. So what's the best way to do that? This equation here. So notice if I put 0 in for r, I would get 0 squared, and then it's multiplying all of those other terms. So the volume as r approaches 0 is 0. If I were to try putting 6 in there, I'm going to get 0 as well, because negative 5/3 times 6 is negative 10, and then I'd have 10 minus the 10, so I'd make that term 0. It would make the height of the cylinder 0. So that's going to give a volume of 0. And then we have to do it for r equals 4. So just imagine going pi times 4 squared times 10 minus 5 over 3 times 4. And what do we get for our max volume? Let's see here. Pi times 4 squared times, in brackets, 10 minus 5 over 3 in brackets times 4. Close that bracket. There we go. 167.6, let's say. And what's that going to be? Centimeters cubed. Okay, obviously that's bigger than the 0 and the 0 at the endpoints, so there's our max volume. And we can say, therefore, max V equals 167.6 centimeters cubed when R is equal to 4 centimeters, and therefore H is equal to 10 minus 5/3 times that 4. I'm just using this formula right here to get the height. Minus 5/3 times 4 gives that, and we'll go math and we'll fraction that, 10 over 3. So find the radius and the height of the right circular cylinder of largest volume that can be inscribed inside a right circular cone with radius 6 centimeters and height 10 centimeters. Okay, and so the radius and height are 4 centimeters and 10 over 3 centimeters of that right circular cone. Okay, and we can also verify this if you wanted to look at the V function. I have to use y and x in the calculator, but y really takes the place of V, and x takes the place of r, so it would have to be, what's the easiest way to type this in? Well, we could just do pi r squared times the 10 minus, in brackets, 5 over 3 times r, which is x. Okay, so there's my volume versus radius. And the interval for the radius was best between 0 and 6. And I got a max volume of, what was it? $167, so maybe I'll do a y max of 200 and see if that shows the graph. The best, there we go, look at that. Perfect. And so where is our maximum? We're to the left of the top of the hill, right down. You go to the right of the top of the hill. Yes, just go close to the top of the hill. There we go. Maximum 4 and 167.6. Looks good. Okay, so there's example 1, everybody. As mentioned, I don't think we can do them all right now. I'll send you more later if you'd like. I do want to definitely do one of these ones, like 4, 5, or 6. Okay, questions 4, 5, and 6 are actually really, really similar. So let's start with number 5. This one here. And it says a man is on the bank of a river that is 1 kilometer wide. He wants to travel to a town on the opposite bank, but upstream, 1 kilometer upstream. He intends to row on a straight line to some point P on the opposite bank and then walk the remaining distance along the bank. To what point should he row in order to minimize travel time? Minimize travel time. If he can walk at 5 kilometers per hour and row at 3 kilometers per hour. Okay. So we have a river, and it is 1 kilometer wide. And we have the man here. He's on the bank of the river that is 1 kilometer wide. He wants to travel to a town on the opposite bank, about 1 kilometer upstream. So let's just say it's over here. This is the town. And it is 1 kilometer upstream from the man. Okay, he intends to row on a straight line to some point P on the opposite bank and then walk the remaining distance. Okay, so he's going to row to some point here, P, and then walk this remaining distance. Okay, and the question comes down to where is the best place to land his boat to minimize the travel time? That's what it's coming down to. Okay. Okay, so to what point should he row in order to minimize travel time? If he can walk at 5 kilometers per hour and row at 3 kilometers per hour. Okay, so let's sort of fill in our diagram a little bit more here. Like we can go like this. We know this is going to be 1 kilometer. And he's landing his boat at point P. And we can say, hey, we don't know how far the point P is away from this point that is directly across from the man. So we call this little distance x right here. And we do know that from this point right here that's directly across the bank from the man all the way to the town, that's 1 kilometer. And so if the distance to P is x, then this little distance would be the 1 kilometer minus that x. So we're starting to get some values here. Okay, and so he's going to row this distance d, that's the distance that he rows, and he's going to walk this distance 1 minus x, that's the distance that he walks. Okay. And the formula that we're going to end up using a lot in this question, guys, is distance equals speed times time. And then in its other form, time is equal to distance divided by speed. Okay, because we want to minimize his total travel time. Okay, so his total travel time is equal to his time for rowing plus his time walking. Okay, so in symbols, we can call this capital T, and we can say his time it takes to row across is T subscript R. Add that to the time it takes for him to walk the rest of the way to the town, T subscript W. So his total time is going to equal, remember, time is distance over speed, so his time for rowing is the distance he has to row divided by his rowing speed, plus the time it takes for him to walk is the distance he has to walk divided by the speed at which he walks. And they give us a walking speed and a rowing speed. The speed for rowing is, you can row at 3 kilometers per hour, and the speed for walking is 5 kilometers per hour. So here's what we know so far. His total travel time will be equal to his distance rowing. We don't have an expression for that yet, but his speed for rowing is 3 kilometers per hour. The distance that he has to walk is 1 minus x, and his speed for walking is 5 kilometers per hour. So we just have to get an expression for the distance that he has to row in terms of x, and we'll use this little 90-degree triangle, and we will go that distance rowing squared is equal to 1 squared plus x squared, Pythagoras, right? In this triangle right here. Okay, so the distance that he has to row is equal to the square root of 1 squared is 1, and x squared would remain as x squared. So that's what has to go in for the distance he has to row. Square root of 1 plus x squared. Okay, and there's our total travel time function, and we want to minimize that. Okay, so we want to find the smallest travel time. So we should come up with an interval for our x value there. X has to be greater than or equal to 0. X has to be greater than or equal to 0 because we wouldn't want point P. We wouldn't want to send point P this way, right? That wouldn't make any sense. Moving away from the town, we're going to be wanting to head to the right. Okay, so X has to be greater than or equal to 0 and less than or equal to 1. Okay, we wouldn't make X bigger than 1 because that would mean that he's rowing over here past the town and then walking back to the town. That doesn't make sense either. Okay, so it's got to be somewhere between 0 and 1. There's our interval. And so then what do we have to do? We have to find the critical points of this time function and then test the endpoints and the critical points. Okay, so that means we need to find the derivative of this. Okay, so I'm just going to write this in a slightly different way here first to make it a bit easier to write the derivative. So I'm going to put a 1/3 in front, and I'm going to go 1 plus x squared and have that to the power of 1/2, it's the square root, plus I'm going to then divide the 5 into both of these terms, so that's 1/5 minus x over 5, or how about 1/5 x as well. Okay, now let's do t prime. I'm going to go 1/2 times 1/3, which is 1/6, and have 1 plus x squared, and then 1/2 minus 1 is -1/2, and then we have to multiply by the derivative of the inside, and the derivative of the inside is 2x. Okay, so there's the derivative of the first term. The derivative of plus 1/5 is 0, and the derivative of negative 1/5, x is negative 1/5. Okay, so there's our derivative. We need to know where this does not exist and where this equals 0. Okay. So let's set it equal to 0. First of all, 2 into the 6, we'll just leave a 3 on the bottom. So on the top, we are going to have x. On the bottom, we're going to have 3. And then we will have 1 plus x squared to the positive 1/2, which I guess we could just write as the square root like that. That looks good to me. Minus 1/2 equals 0. Now, does this derivative not exist anywhere? Are there any problem points for x? Is there anything I can put in for x to make a negative under the square root or 0 on the bottom? No, there's not. Because x is being squared, so it's the lowest it can be is 0. Otherwise, it's positive. Okay, and even if it's 0, we would have 0 plus 1. Okay, so this function exists everywhere. There's no problem points for x. So let's just solve this. To find the critical points, so I just added the 1/5 over to the other side, and now I'm going to cross multiply and get 5x equals 3 times the square root of 1 plus x squared. And maybe we could square both sides to get rid of the square root. And we will get 25x squared equals 9 times 1 plus x squared. And we get 25x squared equals 9 plus 9x squared. Subtract 9x squared from both sides, and we will get 16x squared equals 9. So x squared equals 9 over 16. So x is equal to plus or minus the square root of 9 over 16, which is plus or minus 3 over 4. And the interval is x has to be between 0 and 1, so we'll reject the negative answer. And we will say x equals 3 over 4. Reject negative 3 over 4 because it's not in the interval. Okay, so let's go up here then, and we will test our endpoints and critical points to see which one gives us the minimum travel time here. So we're interested in the time when x is 0, interested in the time when x is 1, and the time when x is 3 over 4, right? Okay, so which one gives us the lowest time? We would have to plug all of those times in here. So here's what I'm going to do. I'm going to type that into the calculator. Square root of 1 plus x squared divided by 3 plus 1 minus x divided by 5. And let's graph that. And we'll go window. X needs to be between 0 and 1. And maybe I'll just go up to 100 for now and see if we can see the graph like that. Let's try to calculate 0, see what that does. Okay, and so remember that this is time in hours. So when that x value was 0, we get 0.53 hours that it takes. When the x length is 1, it takes 0.47 hours. And is it our critical point that gives us the lowest time? 3 over 4. We get a time of 0.46. Repeating, it looks like. Let's check out that 1 again, 0.471404. Okay, so it's close between those two, but this one is the lower time. Okay, so maybe to get a better look at the graph here, maybe we could do window. Okay, there you go. So it's very close between that endpoint and the critical point. If we go and find the minimum, oh, I don't think I did that quite right. Oh, sorry, yeah, the minimum's over here, right? At 0.75. There we go, much better. Okay, so 0.75 and then that 0.46 repeating, and there's the minimum. Okay. All right, so that means our x value has to be 3/4 or 0.75, which is 0.7 of a kilometer. Okay, so that x distance, point P, needs to be 0.75 kilometers downshore from this point that's directly across from the man. Okay, so we can think of it that way. Or you can think of it as, if we did 1 minus 0.75, he would be 0.25 kilometers away from the town. Okay, so to what point should he row? He should row his boat to a point 0.25 kilometers away from the town. Okay, so I always like doing this question because it always ends up on the unit test for this unit. And so there's another one just like it. Again, I'll send you a document with all of these notes filled out, and I'll try to do some more videos of them for you soon. Okay, in the meantime, here are some more extreme value problems that you can try. And of course, I do have that handwritten answer key that shows the answers to these. But these ones are good. Page 214, numbers 13, 20, 21, and 22. And I think this one is just like that last example that we did. So there's one there for you to try. Okay, guys, I will send you another video soon.